Welcome to this video on the flywheel Viva Voce, focusing on determining the moment of inertia. We will cover key concepts and practice questions related to this classic physics experiment. Let's begin the practice questions. The primary objective is to find the moment of inertia of the flywheel, using the conservation of mechanical energy. The total initial energy supplied to the system is represented by the gravitational potential energy, mgH. The moment of inertia, I, in rotational motion is analogous to mass in linear motion. Importantly, the moment of inertia remains constant, regardless of the hanging mass used. The string detaches so the flywheel rotates freely, allowing us to calculate energy lost to friction. Counting the rotations after detachment helps determine the work done against friction. The vernier caliper is the instrument used to precisely measure the axle's diameter. The standard SI unit for moment of inertia is kilogram-meter squared, kilogram-meter squared. When the flywheel stops after N2 free rotations, its kinetic energy at detachment equals the frictional work, N2W. The angular velocity, omega, relates to linear velocity, v, and radius, r, by the equation omega equals versus over r. The term N1W in the energy equation accounts for energy dissipated by friction during the mass's fall. A major source of experimental error is the inaccurate timing of the falling mass, as time is squared in the final velocity calculation. We calculate final linear velocity, v, using the relation versus equals 2h over t, assuming constant acceleration. Concentrating mass at the rim would increase the moment of inertia. The flywheel experiment is based on the law of conservation of mechanical energy. As the mass falls, gravitational potential energy transforms into kinetic energy, rotational kinetic energy, and heat due to friction. The string must slip off to allow the flywheel to rotate freely under its own inertia for accurate measurement of frictional losses. The variable N1 represents the string wraps around the axle, and N2 is the free rotations after detachment. Linear velocity, v, is calculated as twice the average velocity. We find angular velocity, omega, using omega equals versus over r. The moment of inertia does not change with a heavier hanging mass. The mass is concentrated at the rim to maximize the moment of inertia and rotational kinetic energy storage. A vernier caliper is crucial for precisely measuring the small axle radius. Timing the fall is the most significant source of error, because small errors in time are magnified in the velocity squared term. Here are the key experimental formulae. The moment of inertia, I, is calculated as mr squared times the quantity g over a minus 1. Angular velocity is omega equals versus over r. Final linear velocity is versus equals 2h over t. Frictional work, W, is rotational kinetic energy divided by N2. The energy conservation equation balances potential, kinetic, and frictional losses. Thank you for watching this video. Stay connected for more physics tutorials. Like, share, and subscribe.